Anyway, so let's get going here. We will continue talking about assignment number 2 today. Remember that is due February 20th at noon. And then we will continue with talking about the bootstrap and the lecture notes. Are there any questions? Okay, so let's take a look at problem number 2 quickly. Just want to make sure that there's no misunderstandings about what problem number 2 is discussing or how to do it. So this is a frequently used data set. It's a data set of CD4 counts, I guess.
Problem number 1, when asked to value the probability of any seed for
I gave you a seed for part E. Part F, you don't need a what?
What about C and D?
And you don't need one because you're listing out all possible values of T star. You're coming up with the exact distribution, not a Monte Carlo simulation version of it. That's why there's no seed. And that's part of the big purpose of this problem, so that in a lot bigger data set setting, you're not going to be able to list out all possible values of T star. But since there's only 5 observations here, you can. And so this allows you to see then what Monte Carlo simulation is trying to do for you. It's trying to estimate the exact distribution. We can talk about it more after class if you want. Were there any other questions about problem number 1? So CD4 counts. So this is one measure that people use to determine basically the onset of AIDS. As your CD4 counts go down, it's kind of a measure of whether or not you have actually gone from having the HIV to actually then having full-blown AIDS. And so it's kind of an older data set, but I think the main thing in a class like this, provides a place where you can practice using the bootstrap. And so we have the CD4 counts of 20 HIV-positive individuals prior to receiving a new drug. And we're going to let W be a random variable denoting their counts. And then 1 year later, after they've been receiving this drug, we have a random variable Y denoting their counts. And so the purpose here is to estimate the Pearson correlation coefficient between the counts at the 2 different time periods, simply. Okay? Now, in a setting like this, when you actually take resamples, where before with the AC data, we had one vector of data, and we randomly sampled from that vector. And that was equivalent to, let's say, randomly sampling from our actual observations. Now here we essentially have, you can almost think of it as almost 2 vectors of data, or let's say at the baseline, do I call it baseline? Or let's say when they receive the drug, and then 1 year later. And so we still resample the observations like what we did before, but now we are sampling pairs of data. So now when you take your resamples, you have to, let's say, take W1 and Y1 together. You have to take W2 and Y2 together when you're taking your resamples. You're resampling observations. Equivalently, you can think of it as you're resampling rows of your data set. Okay? Any questions about that? So what I want you to do then in part A is to construct an R function that will calculate the correlation, just a regular old Pearson correlation that you learned about in your first stat course, and can also be reused with the boot function when resamples are taken. So if you remember with this boot function, we need to construct our calc.t function a certain way, where the first argument is the data that you pass into it, and the second argument is the indices. In our case, it would be essentially the row numbers to take as a resample. Let's see. Also, what I want you to do is calculate a jackknife estimate of the variance for the Pearson correlation. So this function will return 2 things, the Pearson correlation and a corresponding variance estimate. Okay? To give you some check figures to make sure that you got it right, here are some actual numerical values. If you're not getting this, you're not getting the problem right, unless I made an error. Hopefully that didn't occur. But if you're not getting this, you need to let me know. and I'll help you, okay? Because if you don't get this part right, your whole rest of the problem's going to be wrong. Okay, so problem number 3 then. Let's run the actual boot function on your calc.t function that you created in A. Save the results into an object called boot.res, for the lack of a better name. And print boot.res. Use r equal 1999 and seed value 8199. So again, use set.seed right before you use the boot function. And that way everyone will get exactly the same answer. Make my grading life much easier. Now, whenever you print off results from the boot function, if you remember from last time, you have some information that's printed off, including something that gives you a bias estimate and a standard error estimate. And what I want you to do is take the stuff that's in boot.res and show me how the bias, the standard error, is actually calculated. We actually did this in the notes, so it shouldn't be too difficult. Take a look at page 36 in the notes. Next, I want you to create a data frame that basically emphasizes the multinomial format to our resamples. So the first row of this data frame is going to be correspond to resample number 1. I want you to tell me how many times that the W1, Y1 pair was observed in that resample. Do the same thing for W2 and Y2, all the way down to W20 and Y20. And the last column of the data frame, put in what your row hat is, which is your estimated correlation. Obviously, there would be 1,999 rows in this data frame. Just print off the first 5 rows. That's all I need to see. Part E, then, let's find some confidence intervals. So far, we've only talked about the basic bootstrap confidence interval. Today, we will talk about the studentized interval and probably also the percentile. We may or may not get to the BCA interval. So find these confidence intervals for the correlation coefficient. Use the boot.ci function. That would be the easiest way to do it. And last time with the basic interval, we've used both boot.ci and essentially what you can say is by hand calculations, but using the computer. Make sure you do still know how to do those by hand calculations so that you're not necessarily just relying on the boot.ci function. Part F gives us some other intervals, non-bootstrap intervals, that we can compare to. And so what I'm presenting here are the 2 most commonly used confidence intervals for a Pearson correlation coefficient. And these actually rely on asymptotic methods, in case you never knew that. And so the purpose here is to introduce what the intervals are, and just to make sure you have at least a little bit of an idea how they come about. I'm not necessarily asking you to go through a full derivation, but I want you to at least have a little bit of an idea, because it's good that you understand what symbols such as this actually mean. The first method relies on basically using the central limit theorem, a multivariate delta method, and one can actually show that the square root of n times row hat minus row converges in distribution to a normal random variable with a mean of 0 and variance of 1 minus row squared at quantity squared. Okay, you don't have to show that part. But what I want you to do is take that result then, that approximate normality, and show then how essentially a confidence interval of this form will be derived. Okay? Shouldn't be too difficult. It's very similar to what we did for the confidence interval for sigma squared, that asymptotic interval, where I gave you essentially this kind of result here, this convergence and distribution result. Go from there to the confidence interval. Okay, then calculate it for the CD4 data set. Now, one can also show that if you take a little transformation of row hat, please note the little error there. I put hats on too many different places, so remove the hats on the second set of rows. This transform row hat, this whole quantity converges in distribution to a standard normal random variable. This transformation here is called Fisher's transformation, or the Fisher transformation. Anybody seen it before? Or look maybe familiar? I would think that this is probably the most commonly way that people do confidence intervals for a Pearson correlation coefficient. So sorry you never saw it before. Because it's the best asymptotic method to do it. And the reason why is that notice up here for the original interval we have a row there. Okay, so eventually at some point you're going to have to plug in an estimator, and so that's why you see an estimator right there. Here, notice you don't have any kind of row. So the variance is actually a constant. That's actually helpful, because now you don't have to worry about estimation of that. If you did have to worry about estimation, you're adding some additional variability that you have to worry about. And so with this Fisher transformation, then what you can do is, first of all, find a confidence interval for 1/2 log of 1 plus rho or 1 minus rho. Find a confidence interval for that based upon this nice little result. Then use the inverse transformation. We kind of talked about this a little bit on Tuesday with respect to the basic interval. Use the inverse transformation, and this is what you get for an interval. Oftentimes it's not presented exactly like this if you have by chance come across in another situation, but it's exactly the same. So then calculate this interval for the CD4 data set. Now you should have a general idea if your intervals are correct that you're calculating based upon, well, are they at least somewhat similar to the bootstrap intervals? Excuse me. If they are totally different, obviously you've calculated the interval wrong. If, let's say, the interval goes above 1 or goes below -1, do you think your interval is probably wrong? Yeah. So, while I'm not giving you a check figure here, you should have at least a general sense of, well, is this working or not? Okay. Then, part G, just as a nice little summary, put all your intervals that you've calculated so far in here, put also the length of the interval. And what I would like you to do is simply compare it. So for example, are maybe some intervals wider than other intervals? Are some intervals maybe shifted in one direction in comparison to other intervals? Those are the kinds of things that I'm looking for. There will be some differences amongst these intervals. Then part H. Assess the asymptotic normality for rho hat and also for this Fisher transformed rho hat by using the previous resamples and constructing appropriate plots. So let's just talk about rho hat here. So how would you do that? How would you assess the asymptotic normality of rho hat? Excuse me? QQ plot of what? Of what? Of rho hat? You only have one row hat. That QQ plot's going to be kind of boring to look at. Sorry, I don't mean to make fun of that, but
is it for all 1009?
For all resamples, you could do a QQ plot. Okay. But what's the normal distribution you're comparing to? Okay. I need to know the exact normal distribution that you would compare to. Seriously, we need to be precise here. What would be the exact normal distribution you're comparing to? You're not comparing to this right here because obviously you don't know what rho is. Well, let's talk about this. So, let's see here. These are just some, oops, no, I don't want to do that. These are just some fundamental things that all PhD students need to understand. Oops. Yeah, I do want to have there. I think I've got that right. Yes, okay. We kind of talked about this a little bit for the interval for sigma squared in the Monte Carlo simulation section. Okay. So if I were to write it like this, what should go here? Rho. What should go here? Right? I haven't got there yet.
Square of n.
I said I haven't got there yet. Okay? So notice where n is right now. Okay. Now, if you were to divide this by square root of n, I mean, putting that right there right now, that actually doesn't make sense. Because you're saying as n goes to infinity, you have convergence and distribution, so you can't actually do that. But what you can say then is this. Rho hat, let's say, is approximately distributed for a large sample. Normal rho one minus rho squared, that quantity squared, over n. Right? That makes sense? Silence means yes, always. So if it doesn't make sense, you do need to speak up. Or maybe you need to write it down first and then absorb it. And then think about it. So, I mean, even if you haven't had, like, you know, our Stat 980 class, you talked about convergence distribution at least a little bit in Stat 883. And, well, I'm not asking you to, you know, prove this. All I'm asking you to do is have a basic understanding of what these symbols mean in this class. Because you will see this all over in statistics. And if you're going on for a PhD, just take a look at some articles that might be in JASA, for example. You're going to see this stuff all over the place. Okay, so rho hat is approximately distributed for a large sample as a normal random variable with mean rho and variance 1 minus rho squared, that quantity squared, divided by n. Okay. There's one. Now there's still one more step that we have to do, was I actually kind of said before, in order to do this QQ plot. What is the exact normal distribution that we can compare to? Do we know what rho is? No. Okay, that's the normal distribution that you compare to. You can do a QQ plot. Excuse me? Histogram, yes. And to be honest, I'm not necessarily a big fan of QQ plots. It's easy, very easy to misinterpret them. Histograms, at times, depending upon what your class size is, can be difficult too. You know, what's the other technique that we've looked at? The EDF. So you can plot the EDF versus the CDF. That's my preference. But I encourage you to do two, maybe all three of those, and see what it shows you. I typically will at least do two for practice. Okay. So also do it again with the Fisher transform statistic as well. And this corresponds to some stuff that we actually looked at with the AC data. Remember, with AC data, our statistic of interest, which we call T, was actually the sample mean. And what do? We looked at a histogram of the T stars, and we looked. Well, did it look like it was a normal distribution? No, actually, no. It actually was a little. I believe it was right skewed. And we said, okay, this is how you can use the bootstrap to assess whether or not, let's say, conventional methods that you would have used before this class, if they actually would work or not. And since we see that our statistic didn't have that normal distribution, that causes some concern if, let's say, a regular old t-distribution based confidence interval, which relies essentially on your individual data to be normal before you even apply it, if that would actually work. Or, in other words, does that central limit theorem really kick in or not? Okay, so then lastly here, part I then combines some of the stuff that you did in the Monte Carlo simulation now to a bootstrap setting. So what you're going to be doing is 3 sets of Monte Carlo simulations to examine the true confidence levels and expected lengths of the 6 intervals examined in this problem. Always use 1,999 resamples whenever you're implementing the bootstrap method. Use the exact same resamples for every bootstrap method. There's no reason to do different bootstrap samples or different resamples. Use 500 simulated data sets for n equal 20. Use 500 for n equal 40. Use 500 for n equal 80. And the data should be coming from this multivariate normal distribution here. I purposely picked this multivariate normal distribution because essentially, if the CD4 counts came from a multivariate normal, this is how essentially would be the best fit. So in other words, all I did was I found the mean vector for the CD4 counts, and then I found the estimated covariance matrix. So by doing this, by using this as your simulated data, this will again give you another tool that one could use to determine, well, are these intervals working correctly? Am I truly getting a 95% confidence level if I had data that was essentially very similar, if I simulate data that was essentially very similar to what was observed? And so this is sometimes a technique that is actually used. So now when you simulate the data so that everyone gets the same simulated data, I gave you some seed numbers. And also to help you out, since I understand that, I wouldn't be surprised if a lot of you haven't done simulated multivariate normal data before in R, I show you how to simulate the data for sample size of 20. Okay, just modify it for the other sample sizes. Yes?
So in this program, where do we use the R? Are you find the R there?
Well, I haven't taken the resamples yet. This is just for the actual simulated data, not the resamples. Okay?
So, but not let's say we have 10,000 row and 2.
Well, I mean, in the end, what are you doing here? You are simulating 10,000 observations from a multivariate normal, right?
Yes.
Okay. But all we're doing is we're dividing up to 500 separate data sets. Okay, each is sample size 20. Because when you do Monte Carlo simulation, what do? You simulate data sets under exactly the same settings. And so this is the most efficient way to simulate your data. Rather than simulate one data set, calculate the intervals, simulate another data set, calculate the intervals. We talked about that in the Monte Carlo simulation setting section. That will, in terms of efficiency, in terms of time, it's going to take you more time to do that than it will if you simulate all your data up front. The only time that you should ever simulate your data separately and then apply the statistical methods to each data set like that is, let's say, if you have maybe some very large data sets, or maybe the actual data itself, how you have to simulate it is difficult. Otherwise, you should always simulate all your data up front. You're going to be a lot more efficient. Now, for the resamples, before your first resample, and only before your first resample, here are the C numbers to use to make sure we get all the same results. And then what I would like you to do is summarize your estimated true confidence levels that you get and expected lengths using tables and plots. So what kind of plot do you think would be helpful here? Some kind of trellis plot. But just realize here, we only have, in comparison to the last time, we only have one distribution that you're simulating from. So while you can use my exact same code that I had set up before, just realize, you only have one distribution. So in fact, you don't even have to condition on anything. But when I wrote up the answer key, I just simply took my code from the notes and dropped it into my program, removed that conditioning argument, made some other very small changes, and that was it. Okay. Now let's say that you're doing these simulations and you're worried about some of your results, if they're correct. Maybe you're getting estimated true confidence levels of 0.6 consistently for all sample sizes. What could you do to do a real good check to make sure that indeed what you're doing is correct, or maybe it might be wrong?
Run each part of the code, just go back and see if everything's...
That would be one way, definitely. Definitely that.
Increase the size.
There you go, increase the sample size. All these methods, so the asymptotic method, as n goes to infinity, this is going to work out. And even the bootstrap methods, they're going to get better as n goes to infinity as well. Because remember that f hat becomes a better estimate of f. Okay? We talked about in the Monte Carlo simulation why f hat is a good estimate of f. And so, excuse me. So pick a number close to infinity, but not too close. And you should be seeing your results working out. And I purposely say that because that is an essential tool in statistical research, because you might have programming errors. I think I even mentioned that in the Monte Carlo simulation notes. And actually, when I first programmed this up, I was actually getting some weird results. And so what did I do? I ended up using n equal 200. And I was able to find, oh, I was doing something wrong. Made the correction, and everything's good. Okay? So that is assignment number 2. Are there any questions? Okay. So that takes us back to the notes, page 37. So we're going to talk about the studentized interval. This one and what's called the BCA interval are the two best bootstrap confidence intervals. Generally speaking, in practice, the studentized and or the BCA intervals are the only ones that you should ever calculate. So, if I'm ever in, let's say, attending a seminar and I see someone using the basic interval, or this other one's often called the percentile, that hopefully we'll get to today, a very common question that I will ask then is, why are you using that interval when you know that there are better intervals out there? And usually the response is, no, because this is the only one I know about. It's easy to calculate. Well, that's no excuse. If you have an interval out there that has a better true confidence level and you are a statistician, you use the best interval. Okay, so this interval was developed by Peter Hall. Does anyone know who Peter Hall is? He's actually one of the most famous statisticians out there. He's, I believe, based at University of Melbourne in Australia. But he also has a joint appointment at one of the University of California schools. Unfortunately, I cannot remember which one. But he is quite famous. He is prolific in terms of the amount that he publishes. He will publish in the best journals. And so anyway, so he developed this interval in the 1980s. Sometimes you also hear it referred to as the bootstrap T interval. And the reason why is because basically what he decided to do was, let's try to mimic the usual old t-test statistic. that you, or the studentized quantity, let's say, that you use when working with, let's say, a confidence interval for a mean, or doing a hypothesis test for a mean. You said, so let's try to mimic it. And the reason is because what we're trying to do is come up with you can say, an approximately pivotal statistic. In your SAT 883 class, you've talked about pivotal statistics before. What's the important characteristic about a pivotal statistic? It's not dependent upon any parameters. The distribution itself is not dependent upon any parameters. And remember, let's get back to that discussion that we had with assignment number 2. Why was the Fisher transformation so good to use? Well, remember that variance there wasn't dependent upon any parameters, and obviously the mean wasn't dependent upon any parameters asymptotically. And so what actually that's referred to as, if you form like a usual old, statistic that you take your standardized statistic, take the statistic, subtract off the parameters estimated, and divide by the variance. That's called an asymptotically pivotal statistic. Okay, and well, we won't necessarily get into it in this particular class too much. The bootstrap works better when you have a pivotal statistic. In terms of every resample, you're calculating a pivotal statistic. And all it comes down to is the fact that you have less quantities necessary to worry about in terms of having to estimate. So what Hall said, okay, well, let's maybe try to come up with something maybe that's approximately pivotal. It's not going to be pivotal definitely for every problem, no. Maybe it might be approximately. Let's mimic what Gossett did a long time ago when he had normally distributed data. And so here's our studentized version then of t minus theta. I'm going to call the whole thing z. So I just take t minus theta, and I divide by what is the estimated variance of t minus theta, or equivalently the estimated variance of t. We can put this into a statistical function form similar to what we've done before. So t itself can be thought of as basically a function of your EDF. Theta is a function of your CDF. And since we are working with an estimated variance, since that has to be, this is dependent upon our sample only, and so it's dependent upon then the EDF. And since we're talking about the studentized quantity here, whenever usually it's more so in a STAT 801 or 218 like class, I like to bring this up. The studentized, the t statistic was developed by William Gossett. All of you know the story behind him, how he worked at Guinness Breweries in Dublin. Well, about 3.5 years ago, I visited Dublin for a conference. And as any statistician should do when they are at a conference, they go to Guinness and take the tour. And at Guinness, kind of in their basement, they have a variety of things on the wall to honor famous people who have worked at Guinness over the years. And here they have Gossett, and notice it says he's a statistician. I was very tired that day, so that's why I wasn't looking very good, still getting over the jet lag. So this was actually the best of many pictures that my wife took of me that day. Okay, so just a little side note. Okay, so once we have that statistic then, I don't know what the distribution of z is. I can still, think about it has some kind of distribution. I can think about finding quantiles for that distribution as well. So just like in a derivation for a confidence interval for mu, your population mean, where in that case you do know the distribution, what we can do is then derive a 1 minus 2 times alpha 100% confidence interval for theta. I could ask you to do this on a test. It shouldn't be difficult. If you do have questions about it, come talk to me after class. But this is what it looks like. You have your statistic. You subtract off the 1 minus alpha quantile from the distribution of z. Again, I'm not specifying what that distribution is. It may or may not be normal. Probably won't be normal, because of course there's never anything that's exactly normal. Then I take the square root of the estimated variance. That's my lower bound. My upper bound is exactly the same, but now I work with the alpha quantile. And so again, as what we've seen before, notice how the upper quantile is in the lower bound, the lower quantile is in the upper bound. So that's my confidence interval. I can calculate T, I can calculate V, but can I calculate Z, the quantile? No. I don't know exactly what that distribution is. So, coming into the rescue then is the bootstrap, because the bootstrap allows me to estimate it. And so that all we're going to do for the studentized bootstrap confidence interval is replace this actual quantile from the distribution with an estimate obtained from the bootstrap. So this is how it's done. So now instead of having Z, suppose we have Z star, which is just T star minus T over V star square rooted. It's very important that you realize that there's a star on the V. So what that means then is that for every resample, not only do you have to calculate T, but you also have to calculate V. That's why in that assignment number 2, remember I asked you to find a function that calculates rho hat and also the estimated variance of rho hat. So that's going to lead you to then being able to calculate the studentized interval. And so to emphasize the point then, notice here when I write out the statistical function version, you can see that T star, of course, now is essentially your statistic that's calculated on your resamples. So in other words, it's using then your EDF from a particular resample. Both for T and V that happens. So that then, all we do is we replace this 1 minus alpha quantile and the alpha quantile from the distribution Z with now the R plus 1 times 1 minus alpha ordered value of Z star, calculated for your capital R resamples. And we do a similar thing then in the upper bound. And that is your studentized bootstrap confidence interval. Are there any questions? So to help you think about this interval intuitively and its properties, notice in this interval, again, you have this variance that's calculated for separately for every single resample. It's in the denominator of Z star. Do you see any potential problems that could pop up? Excuse me?
It has to be different from 0.
I'm sorry, I can't hear you.
I mean, the variance has to be different from 0.
It has to be different from 0, yes. Let's say that you have a resample that ends up resulting in maybe the same value of y many times. What do you think is going to happen to that variance? The variability is going to be smaller. So look what happens then to Z star when you have a small variance. Z star is going to blow up. Okay? Now, if Z star blows up like that, what's going to be the effect then on this interval? If, let's say, it happens a number of times. Look how we calculate the interval. It's going to be wide. So the one really, while the studentized interval works rather well, if you remember the Monte Carlo simulations for the sigma squared example, we saw the studentized interval work well. What was the problem with it? It was often very wide. And so that this is the one defect of the studentized interval. While its true confidence level might be good, it's often very good, it can be quite wide because of what we just talked about. Now, an interesting thing about this interval is that, you know, if you were to do the regular old interval for mu, you know, you would take, let's say, y bar plus or minus the value from your t distribution times s divided by the square root n. How would you find then this t distribution quantity? Well, hopefully you would just go to R or even Excel and calculate it there. But what's often done? People go to a t table to do that. So they go find a piece of paper that has all these numbers on it, and they find the correct value. So essentially, what people often think of then this interval is that you're forming a new t-table, essentially. Your own personalized, let's say, t-table for a particular problem. Because all you're doing is you're trying to figure out, well, what do I put in there for that distribution? So, just another way that people think about this kind of interval. Well, what should you use for v, though? So we need to actually specify the variance of a statistic. And depending upon how many years you've been in our program, you might be thinking, well, yeah, I can calculate a variance. Big deal. For example, I know what the variance of y bar is. Well, it's sigma squared over n. I can derive it. I can estimate it with s squared over n. Well, sure, you can do that with simple statistics, but not necessarily for even a little bit complex statistics. You might be thinking, well, if I can assume that, let's say, my y's are distributed gamma, well, I know what the variance is for a gamma distribution, so I probably could actually derive it with the variances for my statistic of interest. The problem is we're not making any of those kinds of assumptions here. We're not assuming any kind of underlying distribution for f. And so figuring out, exactly what that variance should be that goes in that interval is not necessarily a simple thing. So what can you do? Well, there are times, like for a sample mean, where you can come up with what the variance should be. You could use the parametric delta method. Awesome. So suppose you derive the asymptotic distribution for t, which would include some kind of variance, but maybe what you're really interested in is some function of t. Well, use the delta method to figure out, well, what to use for that variance. We've talked a little bit about the non-parametric delta method. And so essentially that's what we will be using often, where we will use a jackknife estimate. And in fact, you could use a bootstrap too to figure out what v is, as we discussed last time. So we will primarily be using these when something like this is available, or this is available. I'll show you that too. But the most general approach is to do these last two. Well, also in that z star, remember you have to calculate the variance separately for every single resample. So what can you do? Well, if there's a simple derivation for, let's say, y bar, well, then there should be a simple derivation for y bar star. So for example, if your statistic was y bar star, we'll just use s star squared divided by n. You could still use some kind of parametric delta method approximation. So for example, excuse me. So for example, like well, I'm not having you do this for assignment number 2. We said that essentially the asymptotic variance of rho hat is equal to 1 minus rho squared hat quantity squared over n. Okay? So if that's my asymptotic variance, how about I just put a star here, and I put a star kind of there, and I could use that. That's simple. But again, as n goes to infinity, that's what this is trying to do. So what else can we do? Well, you can use a jackknife, but now for a resample. So let's say you get your first resample, and then you use the jackknife to find then the estimated variance for your statistic in that resample. So notice what this is doing then. is adding essentially an extra layer of resampling to this whole process, if you think of doing the jackknife as resampling. Well, you could also do a bootstrap estimate, meaning for, let's say, your first resample, now you're going to take, let's say, we'll use a different letter here. You're going to take capital M different resamples from that first resample, calculate the estimated variance based upon the bootstrap. So that's an example of what's called the double bootstrap that we briefly talked about before. We'll talk about it a little bit more shortly. So, for every resample, you're going to need to calculate Z star. I purposely put a subscript R there to emphasize this for, let's say, little r equal 1 to capital R. And there's your essentially your studentized quantity that you're calculating for every single resample. Again, to emphasize, here's a little r, here's a little r. And so that then your interval, your studentized interval, would look like this, where you have V jack, the square root of it, in for the variance part, and these Z stars come from above. If you use the bootstrap, a very similar interval will be calculated too, but now you have a boot in there. Perhaps this is overemphasis, but I do want to do want to do it to make sure there's no confusion. So we need to calculate for the R3 sample V star boot. If I were to actually put this into an equation form, this is what it will look like. What it will look like if I were taking capital M resamples from the R3 sample. So it's just your standard old sample variance formula that we've seen before. But what's new is, notice how I have 2 stars there? Because this is to emphasize, okay, this is coming, it's a resample from a resample, you're calculating this. So the RM value of T star star, we need to go in there. Then the mean for the R3 sample, the mean of all your M resamples in terms of your T statistic will be T star star bar. How many total resamples then are you taking? Well, remember, you have your original R resamples that you're taking, and then for each of those original resamples, you're taking M more resamples from it. So R times M, total resamples from that second layer. So in total, your number of resamples that you will be taking R times M plus R. That's a lot. Can potentially be a lot. So you put some numbers in there. Suppose capital R is 4,999. Suppose M is, we'll just make it simple, 999. That's a lot of computer power that's needed to necessarily do that. Depending upon your statistic, it may or may not be that bad. But at least when Davison and Hinckley's book was written, and also when Efron came up with these ideas in the late 1970s, imagine telling someone that, first of all, not only are you going to take capital R resamples, but now you're going to have to take capital R, M plus R resamples. They'd probably be laughing at you. It's like, that's not practical. No one can do that. No, not back in the late 1970s, but today we can. Okay, any questions? Let's see here. Let's get to an example then. So it's with the AC data again. So we are on page 41. So the first thing that I want to do is show you, well, how would I use the boot function? So I'm going to set a seed so I can reproduce my results. Again, the overall goal is to calculate the studentized interval. Use a boot function. I'm going to pass in my data into a function called calc.t. 4,999 resamples. Sim equal ordinary means I'm using just regular old non-parametric bootstrap. Put the end results into boot.res. So let's take a look at calc.t. I pass in my data. I pass in my indices for every resample. The first thing that I typically always will do is find my resample data. Next, I need to calculate my jack. I'm going to work with the jackknife here. I need to calculate my empirical influence values, the like LJs. I need to calculate them for every single resample. So I use that EMP-INF function that we saw at the end of last class. I pass in my resample data. Then I need to write a new function that calculates my statistic. I can't use this same function because I'm already inside of it. So I come up here to calc.t2 for the lack of a better name. Similar format as before. I pass in my data. I pass in my indices. I find what will be equivalently my resamples. I calculate my statistic of interest. I specify for my statistic type, I'm working with indices, and I want jackknife estimated empirical influence values. With those empirical influence values, I can find my VJack. And then I return, in the end, my T star and my V star jack. Okay, let's implement this. And it takes a little bit of time, but not too long. And there we go. So here's my output then. Here's my original statistic. Here's my bias and my standard error that we've seen last time. Now, since I'm returning two values from my calc.t, you see a second row in this boot.res output. Here is VJack. Let me actually go over to my notes so I can write on them. So here is VJack. If I can spell. And then this would be then the estimated bias of this statistic for VJack based upon the resamples. And here's the corresponding standard error. So at the bottom of page 42 then, 96.75 is T1 star. 501.26 is VJack 1 star. So I can see those by pulling out the T component of boot.res. By pulling out the T0 component, I get what it is for my original data. And for some reason, I cannot spell Jack. Fortunately, I did not. Well, my wife and I, when we were thinking of names for our children, we thought we really liked Jack, like Jackson. I'm glad I didn't call him Jack because I can't spell it. So we have this information now. Let's actually calculate then the studentized interval. So I need to calculate my Z stars. So what do? I take T star minus T divided by the square root of VJack star. And those are all my Z stars. I'll do a head on that. So so Z1 star is negative 0.506. Remember what I need for the studentized interval. I need two quantiles. So I'm going to set alpha to be 0.025. This will give me, remember, 95% confidence interval. So I say quantile Z star type equal 1, and I get my two probabilities in there. 0.025 and 0.975. Print this off. And this is what I get. For comparison purposes, remember again, we're just calculating a confidence interval for a mean. That's it. So if I were to do this the normal way that you would have done before this class and use a t-distribution, look at what my quantiles would have been. Compare that to what the bootstrap tells me. Yes?
What's type equal 1 again?
There are, I believe, 9 or 11 different ways to calculate quantiles.
Oh,
and the
okay.
way that we calculate is using type equal 1, which is actually uses directly the inverse of a EDF. So you can see how this lower quantile is quite different from what the t-distribution would give you. So if you see those kinds of differences, now you can see why a t-distribution based interval will be quite different from what the bootstrap is giving you. So let's calculate then the studentized interval. So I pull out t from my t0 component of boot res, subtract off the upper quantile, and take it times the square root of, again, notice I go to my t0 component of boot.res, I pull out vjack based upon the original data. That's going to be my lower bound. I do a similar thing for the upper bound, and this is what I get for my interval. 45.83 to 90.5. Okay. To emphasize this now, we have made no distributional assumptions. This procedure that I just showed you for a very simple statistic, the sample mean, can be used with any statistic. And notice, once you understand how the studentized interval comes about, there's no more derivations that you have to worry about. You don't have to worry, essentially, if you use like the jackknife or even the double bootstrap here, you don't have to worry about deriving a variance. That's why this procedure is so useful. And it works. The only thing you have to worry about with the studentized interval is the length. And as long as you have an adequate sample size, that's not going to be too much of an issue. Okay, so an easier way to do the calculation is once you've got the results in boot.res, just simply use the boot.ci function. And for the type argument, before we use basic, now do stud for studentize. And you get, of course, exactly the same thing. Make sure, though, you know how to do the calculations without boot.ci. Now, hopefully when you see this, you'd be thinking, wow, this boot.ci is quite powerful because it can automatically do this. But hopefully, too, you're thinking, okay, well, how did boot.ci know where to find the variance? Calculate for every resample. How did it know that, how we structured boot.res $t? Remember, the first component was the statistic of interest. The second component was the variance, calculated for every resample. Why I purposely did it rather than, let's say, flip-flop the ordering there, is because boot.ci assumes that that's how you structured the results from calc.t. So it makes that assumption. So you can see that if you don't know that, this boot.ci is not going to be working as you would hope. So what sometimes is a safer way to use boot.ci in these kinds of situations, especially if there are times where you might be doing this resampling with more than one statistic of interest. A different way to use boot.ci is to actually tell boot.ci where to find the stuff. So this will give you exactly the same output as what we just got, but now I'm going to specify, well, where is my estimated variance for my original data? Well, it's in the second component of T0. Where is my estimated variance for every single resample? It's in the second component of my T component of boot.res. Where is my statistic of interest? Meaning my T for the observed data. Well, it's in the first component of T0. And then lastly, where is my statistic of interest for every single resample? It's in the first column of my $t component. So this can be helpful at times just to make sure you know boot.ci is looking in the right spot. You're not just playing around with the defaults or hoping the defaults are correct. And if you're calculating, let's say, more than one statistic of interest at a time. Okay, so on page 45 then, excuse me. Here are two plots. The code's in my program. We've done these plots before, so that's why I'm not giving you the code again. And we have an EDF plot for Z star. And unfortunately, I forgot to put a label. I forgot to put a legend. So the red, well, hold on, let me make sure. I'm sorry, the black is for Z star. That's the EDF of the black line is the EDF of Z star. And the red line is for regular old T distribution. Now remember what we saw when we compared the 0.025 and 0.975 quantiles for those two distributions. That the one for Z star was really, really shifted to the left in comparison to what the T distribution would give you. And you can see that right here. And so we see some differences between the two distributions, which again then should cause a little bit of alarm to you that, well, maybe I shouldn't use the T distribution approach. Here's also the histogram too, and we can see differences. Well, how do I do the double bootstrap here now? Use the same ideas. My calc.t function is exactly the, oh, hold on. Let me actually start with the boot.res part. So I say boot. Everything here is exactly the same as what we've seen before, except for look what I have here. I have an additional argument, m. And I say it's 999. You can put additional arguments in your boot function call because there is a ... element to that function. So if you look at the help, you will see ... there. So that's why I can put other arguments in there that are not necessarily specified. And the reason why I want to do that is because I need to somehow tell calc.t how many resamples to take from a resample. So notice up here, I have my m. This has to be after your data and your I arguments. So again, I find my resample. And then, since I'm using the double bootstrap here, I need to do another call boot inside my calc.t function, where look at this, there's my m resamples. Also, I have to specify a new function to calculate this statistic, just like what we did with the jackknife. In fact, it's the exact same function, calc.t2. Then once I put the results into boot.res.m, for the lack of a better name, I simply find the variance of my statistic. Just like what we did in the last class when we were just working with a regular old bootstrap. I put the results into v.boot, and again, look what I return, the mean and the variance. While I'm not going to go through here in class, notice what I do here, I always check my work before I actually use the boot function. And I look, do the results make sense based upon what I know about the data? So I'm not going to actually run this in class here. We're just going to take a look at the results here. Because again, it's a second layer of resampling. And using the code that we had with the Monte Carlo simulation section, I actually timed it. It took on my computer 1.3 minutes. Hopefully it will take a shorter amount of time when you run it. Given I taught essentially now the bootstrap now for about 10 years, and I've used a number of different computers, I always find it interesting looking back, since I did use this same example before in my previous notes. I always like to look at, well, how many minutes did it take in 2005 versus now? And computers have gotten faster, and yes, there is some significant time savings. Okay, so if we print off then the results from boot.res2, again we have T here, and here is V boot. And I can essentially just proceed in the same manner as I did with the jackknife. So for example, this negative 4.812 is Z star, let's see now, 5,000 times 0.025. Last time with the jackknife, we had negative 4.84, so just about the same. The upper bound last time was 1.65, this time we got 1.66. Our interval, again, you can use the boot.ci function to do it the most easiest way. Here's my interval, which, as you might expect, is just about the same as what we had with the jackknife. Last time we had 45.8 to 90.5. So, very close. Okay, so that's how you can do the calculation. Here's something else interesting to look at here. I decided to do a histogram of all those standard deviations that we got from the bootstrap. So we got 4,999 standard deviations, square root of V boot. So this would be square root of V boot, even though I didn't label it like that. And this is what I got for the histogram. So what do you call a histogram like this? Bimodal, yeah. So why do you think this is happening? And we see a lot of variability there. Why do you think bimodalness is happening with this data set? This gets back to something we talked about when I first introduced this data set. Let's take a look at the data set.
That last y value.
Yeah. That can cause a big problem. Notice, I don't want to say a problem. That's what's causing the bimodalness. So notice how this number is twice as much as that number. And that obviously when this number is involved, you're going to have a lot more variability. So that's why you see that. This is not necessarily something to be worried about, but I at least want to point that out, that this is what can happen. Now, before taking this class, you would have estimated then the standard deviation of t to be 39.3, using s divided by square root of n. And again, the bootstrap gave us 38.16. Very similar. Jackknife gave us 38.16. So this is an illustration of why in a classroom setting like this, I like to do what are essentially simple problems to show you that with this simple problem, at least with respect to the variance and the standard deviation, you get just about the same result using this more complex bootstrap or jackknife method versus what you learned about in your first stat course. But also in this simple problem, we can see where we might be worried about using the usual methods too, because we saw that t distribution, it's not going to probably work out well. Okay, so some general comments then. We've already talked about the pivotal stuff. Now, similar to the basic interval, you can work with a transformation of t in the hopes that you get a, we're trying to get essentially a pivotal quantity here with the studentized statistic. And you might be thinking, well, maybe there's some kind of transformation out there of my statistic of interest that might lead to a more or better approximation to a pivotal quantity. In fact, yeah, there could be transformations out there that do that. And if you have that, then all you need to do is now form your z based upon then this transformation. Now note here that this h sub t in the denominator that has a little dot on top of it. This is a common way, maybe you have or have not seen this before, this is a common way to say it's a first derivative. So I'm taking the first derivative of h of t with respect to t. Well, where does this absolute value of this quantity come about? It comes about through an application of the delta method. Then for every single resample, you do what you would expect. You put the stars on the corresponding quantities, you change the theta to a t, and then the actual interval for theta itself then involves using then the inverse transformation of h. Now you can do the interval like this, and the interval will likely be better if you can find the right function, h, okay? I typically don't see a whole lot of people doing it like this. They'll just simply use the regular studentized interval like we just did. It's obviously it's simpler. People who use the basic interval, although they shouldn't necessarily use the basic interval in most cases, I will see them use those transformations to try to get a better interval. And there are some problems where, yeah, it makes sense to use a particular transformation. And so that's why that's done. So we talked about why the studentized interval is one of the two best bootstrap intervals. And we already talked about why it is why. Okay, so the next thing that we're going to do, unfortunately we're out of time though, is we're going to talk about the percentile interval. This is the easiest interval to calculate using bootstrap, but it also, you shouldn't ever use it. It's a shame how often you see people use the percentile interval. And it's simply because it's so easy to do. It's actually quite intuitive to do, but it should not be used. Are there any questions? Okay, and that's it for today.